Okay, this is the first of several videos on derivatives of inverse trig functions for Math 1560, Calculus 1 at U of L for fall 2017. And we'll start with arcsine, right? We always start with sine. It's everyone's favorite trig function. I know there's a cosine camp out there, but we'll start with the sine function. We'll show how to calculate that derivative, and then we'll move on and we'll look at a couple of the other inverse trig derivatives. Okay, so let me remind you about how the arcsine function is defined, right? Because remember, it's supposed to be a function. So how do we define arcsine? And remember, there's another notation for this. You'll also sometimes see this written as sine inverse of x. I've mentioned in class and in previous videos why I don't like this notation, because some people will think of that as an exponent and they'll think of this as 1 over sine, but it's not 1 over sine. That's the cosecant function. Arcsine is the inverse of the sine function. Okay. Now, you want to define an inverse for the sine function and you immediately run into trouble, and I think we've showed you this before, but let's take a look again. Here's a graph of the sine function, right? We can immediately see what the problem is. What's the problem? Well, my function is supposed to pass this horizontal straight line test. It's supposed to be 1 to 1 if I'm going to define an inverse. We can see that this definitely does not pass this horizontal straight line test, right? Take for example, the line y equals 1/2 right here, right? You can see that there are many places where we cross the graph, right? In fact, there are infinitely many places where we cross the graph. So this is a big problem. So how do you actually define an inverse? Well, the way you define an inverse for the sine function is you have to first restrict the domain. I mentioned this in the last video, that one of the things you can do is see if you can cut down the domain, hopefully keep the range, but cut down the domain in such a way that we still get every value in the range, but we only get it once, right? So what's the range for the sine function? The range is everything from -1 to 1. So what values do we want to keep? Well, we certainly want to keep, we want to keep the values starting at 0 and going up to pi over 2, which is somewhere here, because, well, that's the first quadrant. Those are the angles everybody knows, right? Everybody knows the values for 0, for pi over 6, pi over 4, pi over 3, pi over 2, right? If you know any part of the unit circle, you know the first quadrant. So we want to keep those. And so then you might say, okay, well, let's just kind of keep going. But you can see that as soon as you go past pi over 2, you start repeating y values again, right? If I went from 0 all the way up to maybe pi, I get y values repeated, and I'm not hitting any of the negative y values, right? I'm still only getting positive y values. So we don't want to keep anything from between pi over 2 and pi, or we're not going to have a 1-to-1 function. So what do we do from there? Well, we could, I guess, go from pi up to 3 pi over 2, but then we'd have kind of two pieces. We'd have this piece of our graph, and we'd have this. It's nicer if it's all one chunk. So what do? We go from minus pi over 2 to plus pi over 2. We take that part of the graph, right? So if we take this part that's in red, you can see that we hit every single y value between -1 and 1, and we only hit those values once. That lets us define an inverse. And remember, graphically, you can think of the inverse as being reflected across the line y equals x, and here's what it looks like. Here's the graph. So we'll jump back to the slide in a second, but notice, what can we say about this function whose graph is in green here? Well, the domain is everything from -1 to 1, right? Notice that the range for the original function becomes the domain for the inverse. The range for this new function is the domain we chose for the sine function. So the range of the new function is everything from minus pi over 2 down here up to pi over 2 up there. Okay, so this is how we first come up with this function. That's why we see this here. So it's important to remember when you're dealing with the inverse trig functions that they have carefully chosen ranges, right? So the range for the arcsine function is from minus pi over 2 to pi over 2. And that means that if somebody asks you to calculate something like, say sine of yeah, I don't know, -1 over the square root of 2. Well, there are many angles whose sine value is -1 over square root of 2, but you have to choose the one that lives in this interval, and the only one that lives in that interval happens to be minus pi over 4, right? So when you're evaluating the, sine inverse, or if you like arcsine, let's call it arcsine. So when you're evaluating the inverse trig functions, there's kind of a multi-step process. You first have to look for, you look for the related angle in the first quadrant, right? If the input is positive, then that related angle is the one you want. You want that angle between 0 and pi over 2. If the input is negative, well, then you take the related angle in the first quadrant, and you can see all you really have to do for the sine function, at least for arcsine, is throw a minus sign out front. Okay. Now, notice this relationship here, right? There is still this inverse relationship that sine of arcsine, they cancel out. They give me back the same thing I started with. You do have to be a little bit careful with this, because if you do it the other way around, if I do, for example, arcsine of sine, and if I put an angle which is outside of this domain that I've chosen for the sine function, I may not get back what I started with. So for example, if I take something like 5 pi over 6, which is in the second quadrant, I'm going to get arcsine. So sine of 5 pi over 6 is 1/2. But arcsine of 1/2 is not 5 pi over 6. It's pi over 6. So in that direction, things don't always cancel out exactly the way you want them to, but if you do the arcsine first followed by sine, you do get the result that you want, right? So there are kind of two points. As soon as I say that y equals arcsine, well, I'm saying that sine of that angle, y is representing an angle here, sine of that angle is x, but also that this y value has to be between minus pi over 2 and plus pi over 2. Okay. Now, how do we take the derivative of this thing? Well, it's an inverse function, so we take the derivative using the method we developed in the last video, right? So we set g equal to arcsine of x. We're trying to calculate g prime, right? So let's just call this thing y, right? So in fact, just to simplify things, let's let y equal arcsine. Okay? So then we know that sine of y equals x. That's part of the definition of the arcsine function. And so we can take the derivative of both sides, right? The derivative of sine y is the derivative of x. And when we take the derivative on the left-hand side, we have to do, well, you can think of this as chain rule or implicit differentiation, however you want to do it, right? So what is y prime? Y prime is g prime. That's what we're looking for. And on the right-hand side, we simply get 1. Okay. So y prime is 1 over cosine of y. Okay, but I can't leave my answer as cosine of y, right? I'm supposed to give an answer in terms of x. This is supposed to be g prime of x. I've got an answer in terms of y. How do I get things in terms of x? Well, remember, one thing we know about the sine and cosine functions, we know that sine squared y plus cos squared y equals 1. So that means that cos squared y is 1 minus sine squared y. But what is sine squared y? Well, sine of y is x. So if I square that, I get 1 minus x squared. Okay. And now I want to solve for cos y, which means I've got to take square roots. But then I've got an issue. There's a positive root and a negative root. How do I choose a root here? How do I know whether it should be plus or minus? Well, remember, where is this y value? Where is sine of y? Right? So y has to be an angle between minus pi over 2 and plus pi over 2. Right? So where are those angles? Those angles are here. They're in quadrants 1 and 4. What do we know about the cosine function in quadrants 1 and 4? We know that it's positive. So we have to take the positive square root because cosine is positive there. And so what do we get? We get that the derivative of the arcsine function is 1 over the square root of 1 minus x squared. And there we have it. We'll look at a couple more inverse trig derivatives in the next videos.